So stat diagnostics needs to be on. Stat wizards needs to be on. And if you do that one time, it'll always work. So don't get out of there. All right, so now back where we were the other day.
Stat diagnostics.
We'll see here in a little bit. It's going to tell what it's going to do is when we get all the stuff in here and we do our linear regression model, it's going to tell us how good it is. Is it, can we depend on it, or is it not very accurate? We had all this stuff input, I believe. Is that right?
Yeah.
Okay, so I think I've still got it in there. We go stat, edit. I don't. Darn. Okay, I'm going to put it in real quick. And if you don't have it in there, why don't you do the same? So remember that we said one other thing that was kind of important to us. We said that if we're going to make a graph of this, we're going to have an x variable and a y variable, right? The x variable won't always be x, and the y variable won't always be y. The x variable really just stands for any independent variable. The x variable is the independent variable. The y variable is the dependent variable. And you can just about always pretty easily tell which is which by asking yourself a question. In this case, is the broccoli consumption dependent on the year, or is the year dependent on broccoli consumption? I mean, it's got to be broccoli consumption depends on the year. The year in which we're living right now really doesn't depend on how much broccoli we're eating, right? But how much broccoli we're eating does depend from year to year on when we're recording it, okay? When you're dealing with time, which most problems will, time is always going to be the independent variable. I can't imagine a situation where it wouldn't be. So this is going to be t down here, and then the other variable, in this case b, goes on the vertical axis. So this is what we might normally think of as x. That's what we might normally think of as y. And then we said one other thing. When we're putting in the values of x, we don't really need to put in the whole year. We could. That'd be fine. It would work. The calculator would give us the correct answer. But when we wanted to look at the graph, it's going to be in a really inconvenient place on the xy plane. We're not going to get to our x values or our t values until we go clear out to 1,980. And wouldn't it be nice and easy if we could just have them close to home, close to the origin? So instead, we said, let's define x as being the number of years after or since 1980. So then 1980 would be 0. 1980 is 0 years after 1980. 1981 is 1 year after 1980, 2, etc. Right? Makes things a little easier. So then we input all of our years from 0 down to 9. It's much easier if you input all the x variables first. Remember, they always go in column L1. The independent variable goes in column L1. And if I just hit enter between each entry, it just steps down the column. If I hit the right arrow, it'll go clear back up to the top. And now I can fill in the corresponding y values. So, 1.6. Just watch and make sure I'm not making a mistake here. Okay, so we got them in there. So we got all our x and y values in, and then the last thing we did yesterday was we did a scatter plot. This is important for a couple reasons. It's not like the scatter plot itself is that big a deal. It is nice to kind of see how the data is distributed. But what's nice about turning on the scatter plot is if I go to the y equals screen, where I want to put in my functions, if I go up to the top and highlight plot 1, then if I do zoom 9, zoom stat, it's going to do something really nice for me. Remember, it's going to size the screen so my data fits right on the screen. If I don't do that, if instead I don't have that plot highlighted and I hit zoom 9, it's not going to know what to do, right? It's just going to go to zoom standard, whatever it was last time. That's not what I want. If I turn the plot on and I go zoom 9 for zoom stat, now it resizes the screen for me, and I can see the data well represented. When I mean it fits the screen, it's gonna set it up so the data is spread uniformly across the screen, and it's not all bunched up in one little corner. We're not missing some points on the screen. They're all there, guaranteed. So there's our scatter plot. We can see this is what kind of correlation? Positive. Does it seem like, I'm curious what you think. Does it seem like good or bad correlation?
Good.
Looks good. It looks like that follows pretty much a line. It's not perfect, but it's pretty good. Well, let's find out what the function is that matches that. What's the equation of the line that best matches that data? And this isn't just a guess. This is a mathematical technique called least squares regression or linear regression, and it takes each data point, very precisely calculates how that contributes to the line. We don't have to worry about it, though. The calculators can do it all for us. So to find the line, remember we go back to the stat page. Now where? Calc. We're going to scoot over to the calculate menu, and there's all the ways we could check the data. We could do all different kinds of curve fitting. We could fit parabolas or all kinds of stuff. But what are we doing? 4. We're doing lines. We're doing linear regression. So we choose linear regression. It's already preset for us. The X list should say L1. The Y list should say L2, just like we assumed it would. And then when I go down to the bottom and hit calculate, it's going to tell me the best fit line. Now let's just do that first, like we did yesterday. If I hit calculate, now everybody's should look like this. Okay, if I go back to stat, calc, 4. We're going to do that a lot. Stat calc 4 gets us to this screen, right, the linear regression. And then if I just skip everything and go straight to the bottom, highlight calculate and hit enter, it's going to do its thing and actually calculate the best fit line for me. Now look what this says. The line is y equals ax plus b, and then it gives me the values of a and b. A is 0.325, blah, 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 right? That's the slope in this case, isn't it? That's the number in front of x. So instead of m, they call it a. B, the y-intercept, is 1.465, blah, blah, blah. Okay, it gives us out to huge accuracy. So there's the equation of the line. What's this other stuff mean? Well, if you look at the r squared and the r is called the correlation coefficient. And it's essentially just tells you, well, it tells you how good a fit it is, but a better one to look at is r squared, because r squared is always going to be positive. And here's how you interpret r squared. R squared, this is a little bit hokey, but I think it works pretty well. It's telling you the percentage fit. Think of it that way. So if I turn this decimal into a percent, how many percent is that? 0.984.
1%.
Well, almost. It's 98. Well, I mean, hold it. It's almost 1, which as a percent would be almost 100. So if I move the decimal 2 places, that becomes 98.4, roughly. Yes? But it's not. Is it highlighted? Is the plot highlighted? Oh yeah, okay. But if you want to see it again, you gotta highlight it. Yeah, I was just showing you what happened if you did unhighlight it. Yeah. Yes, sir.
So your calculator's gonna have R2 and the R thing?
I can yours. I can fix, so it'll do it also. Yeah. Right when we're done with this, bring it up and I'll get yours set up. So the R squared, it's not like it's that critically important. A lot of the stuff we're going to do this chapter, we're not really going to care about that as much. Later on in the year, we will. But it tells us how good is the correlation. You told me visually you thought it was good correlation, and it is. 98.4% is very good. What would 100% correlation be? Perfect. So then the data points would sit exactly on the line. Okay. If you got something like, say, 60% correlation, that's not as good. Then it's starting to get spread out quite a bit. If you got 20% correlation, that's almost none. That's terrible. Right? So this is very strong correlation, though. It tells us that our linear model is a very good one. Okay, it works well. All right, so now what? We found the model, but rather than just get the equation, that's useful. Graphing calculators they do a lot more than that. With the graphing calculator, if we can actually get the equation graphed, get the function graphed, we can do a ton of stuff with the graph. So let's go back to the stat screen. go stat, calc, 4 to get to linear regression. And then let's go down to this fourth line where it says store regression equation. Okay, that's where we can put in a value of y for the y editor. Okay, and then it'll graph that. So we want to put a y1 in there. Now, if you have an 83, you're going to follow the same keystrokes that I'm going to go through here to get that. It's just it just doesn't show up in as nice a little format like this. But after linear regression, when you choose linear regression on an 83, on the same line, following that linear regression command, you'll put the y variable that we're going to put here. And I can show it to you individually if you have questions on that. So to get a y variable, I think this is kind of where we ended up. You hit variables, the button variables, VARS. You scoot over to y variables. We always want function, so then I just hit enter for function, and now I can choose whichever one I want. For now, we'll just pick y1, but eventually, later in the year, we're going to be comparing different kinds of regression, and we might want to put the linear one as y1 and the quadratic one as y2, and so on, so we can see them visually and see which one works better. We'll just select y1. It puts it in there, and now if I go down and hit calculate, it gives me the same answer as before, but when I go to y equals, there it is. It gives me and it goes on a long ways. I mean, look at that. It keeps a ton of decimal places for both the slope and the y-intercept, right? So it's all in there. You don't have to do anything. You don't have to transcribe it by hand. It puts it in for you. And when I go to the graph, there it is. Now that's kind of nice because we can visually see how the data relates to the best fit line. But once we start using the line, that's our model. That's our mathematical model that we built from regression. We don't really need the data anymore. Okay, we can get rid of that data. So let's go back up to y equals and turn off that plot so we only see the line there. Okay? Now, what we can do with this line, we can do lots of stuff. Now, the reason we use a mathematical model is so we can make good predictions about what we might expect for the amount of broccoli eaten to be in a given year. For example, if I want to know, let's say we want to know halfway through 1984, what's the predicted amount of broccoli consumption at that particular point? Well, then 1984 is t equals 4, right? Or on the calculator, x equals 4. So if I want to know what the y value is, I can go to the second calc screen where I can do all kinds of stuff with the graph. And I'm going to pick the first option, which is value. Okay, so we do that again. If I'm on the graph and I want to ask a question about the graph, I want to ask the calculator a question about this graph I'm seeing, I always go to the second calc. So second F4. Go to that screen, and I get a whole list of stuff I can do. Now, many of these are calculus things that we won't do this year, but some of them are very important to us even now. Like the first one, value. That means what's the value of the function, what's the y value of the function when I pick an x value. And it's going to ask me what x value I want. So if I put in 4.5 and hit enter, well, look what it does. It puts the cursor on the line at that point, but more importantly, it tells me the y value. The y value is 2.93. Okay? Right? Make sense? Now, I got another question for you. Let's say I want to make a prediction for what would typically happen in 1985. So I'm going to put in 5 here for x. And there is a shortcut on this too, by the way. Rather than go second calc, if I just go trace and I type in an x value like 5, it takes me right there. So there is a little shortcut if you want to do that. So trace 5, enter. It predicts a value of 3.0927. So out to 3 places, 3.093. Well, in 1985, we actually got a value of 2.9. Now, which is really a better prediction? This is kind of curious. I want you to think about this for a second. The data that we took suggests that, the data worked out to be 3.5, right? But as a predictive model, the data can be off from the average a little bit, can't it? So what's really a better prediction? Let's pretend, this kind of data, maybe I should have picked a little different example, but what if we were capturing data about something else? Like let's say we were capturing data about, how how many fish were passing by Bonneville Dam or something, right? Something like that. And we're taking, instead of broccoli consumption, we're going to make measurements of those fish, but are the measurements going to be perfectly accurate? Well, no, they're not, right? There's going to be some wiggle room in there where maybe we get too many, maybe we get too few. Any individual measurement is going to have some error associated with it. Just like maybe the measurement of even the broccoli consumption is based on some, I don't know how they did that, but maybe they could have been off a little bit. When I take all that data together and I put it on a line, that line serves to average out the errors, and so the predictions made by the line, by our mathematical model, are actually much better than the individual measurements because they've accounted for the error. That might, and now think about what I'm saying there. That might not seem like much, but that's pretty important. Right? Even if we want to know a more accurate estimate of what happened in 1985, a lot of times the measurement we made is not as good as what the model predicts. Because the model takes into account a whole bunch of data, and the more data you have behind a model, the more solid it becomes. Okay, for example, if I flip a coin 10 times, would it just be ridiculous if I got 8 heads and 2 tails? I mean, it wouldn't be. I mean, if we all flipped a coin 10 times, I guarantee somebody in here is going to have something like that. It's not all going to be 5 and 5, right? You wouldn't want to, stop the presses and, call all your relatives and tell them I flipped 8 heads and 2 tails. That's not that earth-shattering news, right? But if I flipped a coin 1,000,000 times, is it possible I'm going to get 800,000 heads and 200,000 tails? I mean, you might say it's mathematically possible, but it's so fantastically unlikely that it couldn't happen in a trillion different universes if everybody was doing it at the same time. It would never conceivably happen. Why wouldn't it happen? Because when you make that many flips of a coin, you get a ton of data, and the data is always going to converge on the average when you have lots and lots and lots of data. So you're going to get roughly 500,000 heads and 500,000 tails. Is it going to be exactly 50-50? No. You might end up with a few more heads than tails, but you're not going to end up with 80% heads and 20% tails. That is literally, for all intents and purposes, impossible. This would never happen. Question? And you got, if I had, did I start off with 10,000? Oh, 1 million. See, I started off 1 million total flips. 800,000. I started out some big numbers. 1 million total flips. You'd never get 800,000 heads and 200,000 tails. It just could never happen. It's just too unlikely that it's going to skew from the average that far. So what you got here is something that's really an important tool. Now, there's one other thing the calculator allows you to do that's even more important. Pretend we're going back to 1989 and you're a broccoli farmer. You want to know, I want to make a prediction for the next few years. What do I need? Do I need to be buying more fields? What's going on? What's going to be the predicted growth model for this thing? So better than just interpolating.
Please excuse me, direction. The freshman boys dance team needs to be excused at this time and go to room 233, Miss Megan's room. The freshman boys dance team needs to go to room 233 at this time. Thank you.
Okay, so rather than just picking, predicting values that are within our data set, that's called interpolating. I don't care if you know the names really. Extrapolating. If we go outside of that data set and make a prediction into the future, that's more valuable in a way. So let's say I want to go out to the year 1995 and make a prediction about what broccoli is going to be doing based on this model in 1995. What value would I be putting in for T? In 1985.
85?
How many years is that? 95. Gosh, 1995. How many years is that after 1980? 15. Okay, so if I want to find out what it's going to be that far out, I've got to input an X value of 15, but the calculator's not going to like that the way I've got it set up right now. If I go trace 15, it's going to blow up. It's going to say error invalid. And the reason it says invalid is because my window is only going from X values of negative 0.9 up to X values of 9.9. If I want to ask the calculator, If I want to ask the calculator a question about the graph, then the x value I'm asking about has to be included in this window. So if I want to do something like this, I've got to go back to the window and change x max, the biggest x value, to just anything bigger than 15. It doesn't matter. It could be 20, it could be 30, it makes no difference. I'll just put in 20. And now if I hit graph, look what happens. Well, the graph goes off the screen. That's okay. If I want to fix it, I can show you an easy way to do that. But as long as the x value is included, if I go trace 15 now, it's going to give me the right answer. Even though it's off the screen up here somewhere, the y value is still accurate, 6.35. That's 2 places. If I want to see the picture better, there's an easy way to fix it. I can just go zoom 0, which is zoom fit, and it'll resize the screen so the line fits better. And then if I go trace 15, I can actually see the point, but the y value is still the same. Now that's good. That's making a prediction about the future, about what's going to happen based on this model. That's where math models become so valuable. That's how people would, for example, if you want to make a prediction about hurricanes, it's a lot more complicated than this, but all it is, it's a big fancy supercomputer that's got some kind of mathematical model built on data. And if we want to play that model forward, it can make predictions about, where would we expect a hurricane to go or when might one appear. And it's, that's not exactly a very exacting science at this point, but it's getting a lot better. Okay? So this, even though this is a pretty low-level model in a way, it illustrates something that is probably the most important thing that math does, and for many of you, maybe the only really important application of math that you may end up using throughout your life. You may not do a lot of algebra. You may not, honestly, but you're probably going to do some of this. If you've got a job where you're, a kind of a white-collar type job where you're working with data and computers, this is the kind of thing that you're likely to do. And if you're able to do it, that's going to give you a huge leg up on other people. Even if you're not a math expert, that's not your major. If you understand how to do this stuff, and we'll do some of this on Microsoft Excel also, or any of the other spreadsheets that are just clones of that. Being able to do this stuff is extremely important, and it does it very easily, just like it does on the calculator. It's almost the same process. And we'll get a chance in the lab to do that here soon. Okay, questions?
No.
Okay, good. I know I'm about out of time here, so I'm going to wrap around.